First paper that we are going to hear about is type checking CRDT Convergence. George Zakhour, Pascal Weisenburger, and Guido Salvaneschi are the authors. And Pascal is going to give us the talk.
Okay, then thanks for the introduction. And hello, everybody. So this work on type checking CRDT Convergence with Propel is joint work with the aforementioned co-authors, George Zakhour and Guido Salvaneschi. So for George, unfortunately, he is the student involved in this work and he cannot be here today to present due to some visa nonsense, but he's available on Discord, so feel free to discuss with him about this work online. So for the talk, you have to make do with me. Okay, let's start. First, let's assume we have a distributed system. So this is a system where the different machines are on different locations and they communicate through a network. And as you probably know, data replication plays an important role in distributed systems. So this means that the different sites hold their own copy of the same data. Here we have a purple, an orange, and a green copy, but those are all copies of the same document. So all documents contain the same brown box in this picture. We replicate data first to provide scalability, so the data is directly available at every site, and also to increase the tolerance to faults. So in the real world, network connections can drop. Now what happens to the copies when some links in the network break and, for example here, the purple location gets cut off? So obviously there's no way that the purple location can synchronize the changes to the other documents with the other replicas anymore. And there are two obvious options you have here. The first option is we do not allow any location to change the documents anymore until the network is restored. So this will ensure that the replicated data stays consistent, but obviously at the cost of being unable to make any progress on the replicated data anymore. The other option is to sacrifice consistency and let the different machines change their own copies. So from the user's perspective, the service is not blocked, but stays available. So in the example, the orange and the green locations can still synchronize their copies, but the purple location may change its copy independently. But then the different documents are not copies of the same data anymore, but their content can diverge over time. There is a middle ground between strong consistency and availability guarantees, so-called eventual consistency models. And the idea is to allow replicas to diverge temporarily, but as soon as the network is back, we synchronize and get all the replicas into the same state eventually. The problem here is, if states diverge, how can we make sure that we can reconcile the states when the network is back? So one popular way to do this is to use special data types, so-called conflict-free replicated data types, or CRDTs for short. So CRDTs were formally defined in 2011 by Mark Shapiro, and they provide kind of this framework for solving this problem, for allowing availability, but also guaranteeing eventual consistency. And since then, a lot of research went into discovering CRDTs for the various data types. To see how CRDTs works, let's consider a simple example, where we have here these three parties, and they want to maintain a shared counter that is replicated to each of the three replicas. So this specific counter only supports an increment operation, so the value can never decrease. The way you would solve this problem using CRDTs is that first, they would each have their own local counter, and this counter represents the number of increments that have been executed on the specific replica. And then in addition, the replicas also store a counter of how many increments they have received from the other replicas, and they store the value which they saw last. So if the last sync was some time ago, the values can be outdated, but only temporarily until the replicas synchronize again. And the value of the replicated counter is then the sum of all the replicas, local counters, because this is the sum of the increments that happened in the overall distributed system. So here we can see that the data is not consistent. It has diverged in all three parties. Now, how does synchronization work? Well, we can merge two counters by taking the pairwise maximum of the counter vectors. And the maximum ensures that we do not miss any increment, and also that every increment is counted exactly once. So in the example, the purple and the orange replicas synchronize by exchanging their vectors. And what we see here is that after the merge, both replicas are in the same state. But they are still missing an increment that happened on the green replica, and the green replica is missing some increments from the purple and the orange one. Then we perform a similar merge between the orange and the green replica. And now they are fully updated, but the purple one is not yet. So after a merge of the purple with either the orange or the green, all counters are back into a consistent state. So now every replica sees the exact same value of the counter. So what is important is that the state space of a CRDT is encoded in such a way that the merge is always possible and there are no merge conflicts. So making sure that syncing two replicas and merging their state always works and all replicas end up in the same state eventually, for this the merge function has to satisfy certain properties, which are first, the merge function needs to be commutative. So merging state A with B or merging state B with A is the same. Second, the merge function needs to be associative. So merging A with the merge of B and C is the same as first merging A with B and then with C. And commutativity and associativity essentially mean that the order of the merging does not matter. And third, the merge function needs to be idempotent. So if two states are already the same and we merge them, we get the same state as a result. These three properties together are enough to guarantee eventual consistency, and all replicas will converge to the same state. So CRDTs with merge functions that satisfy these properties exist for a lot of different data structures, such as different kinds of counters, sets, maps, and so on. And a lot of research has been done to develop encodings for the different data structures as CRDTs. But guaranteeing that the encoding is correct CRDT so that the merge function satisfies these properties is not trivial and requires manual proof effort for each new CRDT. So a few years ago, Martin Kleppmann, who worked a lot on CRDTs, tweeted that he wrote down some simple CRDT algorithm and he thought it was obviously correct and it was only 10 lines, but then he found a fatal bug only after spending hours trying to prove the algorithm correct. So based on that, he then published a technical report that has some evidence that also others struggle to identify the problem and correct it. So what we provide in this work is a type system that can statically verify that the CRDT implementation does indeed converge. So what we provide at a high level is essentially the following. We offer this type system to check CRDTs, and developers can express the important properties of CRDT merge functions, which are commutativity, associativity, and idempotency in the type of the function. Which means the developer can ascribe a function with a certain property, and if a type checks, it is guaranteed that the properties hold. So the type checker then uses an automatic property proofer to check whether a specific property holds for a specific function. And we implemented a proofer that is tailored to this kind of algebraic properties that we are interested in. And on the other hand, the proofer can also use the properties of the functions that were already type checked in its proofs. So the way this works is that the proofs are constructed when checking the introduction form of a function, and the types witness that such a proof exists. So this enables a form of higher order composition where properties of functions are used to prove properties of other functions. So I will now give you an example for both the orange and the green part. So what we see here is a Scala implementation of a counter from the initial example. If you remember the idea, there was to take a pairwise maximum of the counter vectors. So that's what we do here. The function gets two lists of numbers as input. And if either list is empty, it just returns the empty list. Otherwise, we take the maximum of the first elements of the both lists and recurse on the tails of the lists. The maximum function is defined as usual. I left it out here. What is important is just that the types of the function say not only that this is a function from two lists of numbers to a list of numbers, or from two numbers to a number, but also that the function is commutative, associative, and idempotent. And this is encoded as part of the function's type. So what you also might notice here is that iterating over lists and constructing a new list by applying operations to the elements of both lists is a common pattern. It's essentially zip-with. So we can abstract over this and implement zip-with, which is what we can see here. And the implementation itself is not really that interesting. What's interesting, again, is the properties and the types. So zip-with is parameterized not only over types, but also over properties. So we say that the first argument of zip-with is a function with properties P, which we define to be a combination of commutative, associative, and idempotent. And then the next arguments of zip-with have the same properties P. So the properties of zip-with are parametric on the properties of its arguments. Finally, we can then define the counter merge function in terms of zip width. So we just zip the two lists with max. And because we know max is commutative, associative, and idempotent, we can derive that the composition zip width of max is also commutative, associative, and idempotent. So the algebraic properties we currently support are the ones we've seen so far: commutativity, associativity, idempotency. And we also support the selectivity property, which says that a function will always return one of its arguments. In a similar way, we also support common relational properties: reflexivity, symmetry, transitivity, connectivity, and antisymmetry. So now let's go quickly through the commutativity proof of max. So this max implementation works on bit vectors. And since we declared the type of max to be commutative, our goal is to prove commutativity. So the equation which needs to hold is max AB equals max BA. And we have access to the usual typing context in which we are proving the definition of max. And in this context, we have an equals function, which is a binary relation that is antisymmetric, symmetric, and transitive. So from the typing context, we can also look up the properties of the functions in scope. So for the proof, we also maintain a set of equalities, which also serve as rewrite rules, and a set of inequalities that help us find some contradictions. We then perform a case analysis on the different branches a function can take. So from the first pattern, we can derive a set of equalities and a set of inequalities that hold in the first branch. So here, for example, we know that A is nil. Since now we are inside this recursive max function, the typing context is extended with the fact that max is a commutative function. And then in the end, it follows from the first two cases that B equals B, when A is null, which is obviously true since both sides of the equation are syntactically identical. We then continue to the case where A is a B0 and B is a B1. And since we have in our equality set that equals max xy and y is true, and we know that equals is antisymmetric, symmetric, and transitive, we can then derive that max of x and y equals to y. So this essentially lifts an equality relation defined in the user code into our equality set. And with this kind of algebraic reasoning using these properties that we know, we can prove the goal. So the remaining cases are similar. And this will conclude the proof that max is a commutative function. So we evaluated our approach on 20 common CRDTs adopted from open source projects, and we compared against two automated inductive theorem provers, HIPSPEC and Zeno, and two state-of-the-art SMT solvers that have the ability to reason by induction, CBC5 and Vampire. We checked a total of 91 properties on different CRDTs and the helper functions needed to implement them. So the plot here shows the number of properties that were proven, timed out, or failed. And you can see that our approach was able to automatically prove the three important properties for all CRDTs but one, and it outperformed the existing approaches here. We also compared on a subset of the well-known TIP benchmarks for inductive theorem provers, the ones that encode algebraic properties that we support. And we were happy that on these benchmarks, our approach performs quite well, substantially better than the state-of-the-art that we compare to. So if you want to play around with this, our tool is available open source. We also compiled it to JavaScript, so you can try it out in the browser on propel-prover.github.io. So to summarize, I presented Propel, a type system for checking the convergence of CRDTs. The approach is based on the idea of statically reasoning about algebraic properties and track them at the type level. And this essentially concludes my talk, and I'm happy to take your questions.
Thank you. Questions from the audience? Please state your name and affiliation.
Hi, Tim, Princeton University. So it seems like a lot of these properties have to do also with the monotonicity of the relationship between, like, if you have counters, you don't want to take the min, you want to take the max. Are you also able to check the monotonicity of the system?
That's a very good question. So far, we have the properties that I presented so far that we can check. Looking into monotonicity would also be interesting in this context, of course. So far, we didn't really need him to check the correctness of CRDTs because there you don't really need this property. It's really sufficient that you can check that this is essentially a join in a semi-lattice, so you need these three algebraic properties. And so we didn't look into this yet, but it's definitely an interesting point, yes.
Thank you.
Hi, I'm Shadaj from UC Berkeley. I'm really curious, were you able to use a system to verify sequence CRDTs? Because traditionally those are really hard to decompose into these nice ACI pieces.
Yes, that is true. And these sequence CRDTs are indeed a great challenge also for our system. We quickly looked into that, and so far we have to say that no approach we are aware of can prove them automatically, and this unfortunately includes ours too. But we want to look into that a bit further, because obviously it would be interesting to see how far we can push the boundaries of what we can do automatically also for these list CRDTs.
Thanks.
Any other questions? While Dave is setting up, I have a question for you. So this idea of, proving properties for data structures was also used for like speculative execution and things like this. Have you considered how to apply this technique to those?
Also very good question. So far we really focused on this use case of CRDTs and try to, have something that works really well in that use case. But obviously you're right, it would be interesting to see how this can be applied to other domains too, because I think that there is quite some space to do this. Yeah.
All right, well, Dave is setting up. Thank you.
Thank you.